At 0137 hours on February 1, 1953, the water level at Hook of Holland reached 3.85 meters above the established Amsterdam Ordnance datum. This height exceeded the crown elevation of 87% of the primary coastal dikes in the southwestern Netherlands. The astronomical spring tide peak coincided within 90 minutes of maximum storm surge displacement. The combined hydraulic load surpassed the designed freeboard of every earthen embankment constructed between 1850 and 1952 along a 280-kilometer coastal frontage. Dutch coastal defense in 1953 relied on a dike network built to withstand storm surge events with a calculated return period of 1 in 100 years. The British East Anglian seawall system operated under similar probabilistic assumptions. These structures were earthen embankments with clay cores and grass surfacing. Design freeboard in the Netherlands averaged 0.5 to 1.0 meters above the highest recorded tide since 1825. Post-war reconstruction priorities had delayed routine maintenance on 34% of the Dutch dike inventory. The British defenses had been degraded by wartime neglect and material shortages. Engineering standards assumed that storm surge magnitude would remain within historical boundaries established over 127 years of tidal observation. No provision existed for the simultaneous occurrence of peak astronomical tide and maximum meteorological surge. The safety margin embedded in the 1953 coastal infrastructure was predicated entirely on precedent rather than hydrodynamic modeling. On January 30, 1953, a deep extratropical cyclone developed over the North Atlantic and tracked eastward into the North Sea basin. Central pressure dropped to 968 millibars by the evening of January 31st. Sustained northwesterly winds exceeded 35 meters per second across a fetch of 600 kilometers. The wind stress generated a storm surge that propagated southward through the funnel geometry of the North Sea. Astronomical conditions placed the moon at perigee. The spring tide peak was forecast for the early morning hours of February 1st. The meteorological surge and the tidal crest converged within a 90-minute window. This synchronization was not detected by forecasting agencies. The resultant water level represented a superposition of two independent forcing mechanisms. The combined amplitude exceeded any event in the instrumental record. The surge arrived at the Dutch and British coasts during hours of darkness with no advance warning to civilian populations. Overtopping began along the Norfolk coast at 2300 hours on January 31st. Seawater breached the crest of the Hunstanton seawall and inundated low-lying residential zones. In Zeeland, the first overtopping events occurred at Schouwen-Duiveland at 0045 hours on February 1st. Wave run-up carried seawater over dike crests that had never been overtopped in living memory. The earthen embankments were not armored against hydraulic erosion. Grass surfacing provided minimal resistance to flow velocities exceeding 2 meters per second. Within 15 minutes of initial overtopping, the seaward face of multiple dikes began to erode. Saturation of the clay core reduced internal shear strength. The hydraulic gradient across the dike cross-section increased as water pooled on the landward side. Pore pressure within the embankment rose to critical levels. The earthen structure behaved as a saturated soil mass under unidirectional hydraulic loading. Structural integrity depended entirely on the cohesion of the clay binder. That cohesion was time-dependent and degraded rapidly under sustained flow. Northwesterly winds maintained velocity above 30 meters per second for 11 consecutive hours. The storm surge did not recede with the ebb tide. A second tidal cycle began at 1300 hours on February 1st. The water level remained elevated throughout the intervening period. Hydraulic pressure against the inland face of the dikes persisted without interruption. Drainage systems designed to evacuate rainfall could not cope with seawater intrusion. Pumping stations were submerged and lost electrical power. The polders of Zeeland and South Holland function as enclosed basins with surface elevations below mean sea level. Once the dikes were breached, gravitational drainage became impossible. Seawater continued to flow inland until hydraulic equilibrium was achieved between the sea and the flooded polder. Wind-driven wave action maintained turbulence within the floodwater. This prevented sedimentation and sustained the transport of debris. The duration of the hydraulic loading was the critical variable. Earthen dikes are not designed for prolonged submersion under dynamic wave conditions. The first catastrophic breach occurred at 0310 hours on the Grevelingen dike near Oude-Tong. The failure mechanism was toe erosion followed by rotational slip of the landward slope. Water velocity through the initial breach reached 8 meters per second. Scour deepened the breach channel and widened the gap to 40 meters within 2 hours. A total of 67 major breaches developed across the Dutch coast between 0300 and 900 hours. Each breach followed an identical progression: overtopping, surface erosion, core saturation, slope failure, and catastrophic washout. The British coast experienced 12 major breaches along the Lincolnshire and Norfolk shorelines. Breach hydraulics created localized flood waves with amplitudes exceeding 3 meters. These waves propagated inland at velocities of 5 to 7 meters per second. The structural failure of the dikes converted a gradual inundation into a rapid hydraulic shock. The flood transitioned from overtopping to breach flow within a span of 6 hours. The Dutch telephone network was a landline system with exchanges located at ground level in coastal towns. Submergence of the Zierikzee exchange occurred at 0425 hours. The Middelburg exchange lost function at 0510 hours. 16 primary exchanges in Zeeland and South Holland were inoperative by 0700 hours. Communication between the flooded polders and regional emergency centers ceased entirely. Visual signaling was impossible during nighttime hours. Radio communication was limited to military and maritime frequencies. Civilian populations within the polders had no method of requesting external assistance. Emergency services in Rotterdam and The Hague received no distress calls from the affected zones until after daylight. The isolation was not a failure of preparedness, but a consequence of infrastructure topology. The communication grid was co-located with the population it served. When the population was inundated, the communication system was simultaneously destroyed. This coupling eliminated the possibility of real-time damage assessment during the critical first 8 hours. The rail line between Roosendaal and Vlissingen was submerged along 34 kilometers of track. Rolling stock was immobilized at Capelle and Bergen op Zoom. The ferry service between Kruiningen and Perkpolder ceased operations at 0615 hours due to wave heights exceeding 4 meters and the presence of structural debris in the Oosterschelde. Road access to the islands of Schouwen-Geuveland and Noord-Beveland was severed by the flooding of the causeways. Vehicular movement within the polders was restricted to the remaining dike crowns. These elevated roads became the sole evacuation routes. Debris accumulation and dike subsidence rendered many of these routes impassable by mid-morning. Helicopter operations were limited by low cloud ceiling and high wind velocity until February 2nd. The transportation network that connected the polders to the mainland was designed for economic efficiency rather than emergency redundancy. Its total collapse within 6 hours eliminated the possibility of mass evacuation or the rapid deployment of relief equipment. Relief operations required the placement of sandbags and clay bales to close the dike breaches. Each breach required between 5,000 and 15,000 metric tons of material. Ground conditions in the flooded polders consisted of saturated clay with zero bearing capacity. Wheeled and tracked vehicles experienced sinkage rates of 15 to 25 centimeters per pass. Access roads degraded into impassable mud channels within hours of initial traffic. Amphibious vehicles were not available in sufficient numbers. Material transport defaulted to shallow draft barges operating in the flooded polders. Barge navigation was hindered by submerged obstacles, including fences, power lines, and building debris. The average closure time for a single breach was 14 days. Logistics dictated the timeline. The failure of the dikes was a 6-hour event. The restoration of the dike network required 6 months. This asymmetry reflects the fundamental difficulty of operating heavy machinery in a liquefied soil environment.
Total inundated area in the Netherlands, 165,000 hectares. In the United Kingdom, 64,750 hectares. The Dutch coast sustained 67 major dike breaches and 142 minor failures. The volume of seawater displaced inland in Zeeland alone exceeded 680 million cubic meters. Agricultural land accounted for 89% of the flooded area. Soil salinity in the inundated polders reached concentrations of 8 to 12 grams per liter. Restoration of agricultural productivity required between 3 and 5 years of desalination through rainfall leaching. Structural losses included 4,787 buildings destroyed and 37,000 buildings damaged in the Netherlands. Livestock mortality: 47,000 cattle, 37,000 poultry, 3,400 pigs. The economic cost in the Netherlands was estimated at 1.5 billion guilders in 1953 currency. In the United Kingdom, 50 million pounds. The physical footprint of the disaster was determined entirely by the elevation contour at 3.5 meters above ordnance datum. Everything below that line was submerged. The Delta Commission was established by royal decree on February 18, 1953. Its mandate was to redesign the Dutch coastal defense system to withstand a storm surge with a return period of 1 in 1,000 years. The Commission delivered its final report in 1960. The recommended solution was the Delta Works, a series of dams, barriers, and storm surge gates that shortened the coastline by 700 kilometers and eliminated tidal exposure in the Zeeland estuaries. Construction began in 1958 and concluded in 1997. The UK response was the Thames Barrier, completed in 1982, designed to protect London from a 1 in 1,000 years surge event. Both projects represented a paradigm shift from probabilistic defense to deterministic closure. The 1953 flood terminated the era of passive earthen embankments. The replacement infrastructure was concrete, steel, and hydraulic automation. The system reset was total.